Hi, my name is Sharon. I'm a software engineer at Lyft, and I flew into Berlin from San Francisco. Super excited to be here in Berlin and at Beam Summit. So I work on the streaming platform team at Lyft. And if you're not familiar with Lyft, we are a ride-sharing company in US. So very similar to Uber, but very pink. So our mission, so Lyft's mission is to improve people's lives through the world's best transportation. And to that end, we want to make sure that our users, both drivers and passengers, have an excellent experience on our platform. So to do that, we use machine learning for various features on Lyft. So let's look at some of these use cases. So when you open the Lyft app and when you call a ride, so the Lyft, our service, matches you with a nearby driver, gives you an estimated time of arrival, and also quotes you a price for your ride, among various other things. And we make some predictions about this. So for example, we use traffic, weather, data, etc., to predict what your ETA would be. We look at the demand and supply curves to come up with a fair price. And as you can imagine, a lot of these inputs that go into this kind of decision-making and prediction are constantly changing with time. For example, suppose a train service just breaks down. So if you have been to California on San Francisco, we have this service called Caltrains, which breaks down all the time. So suddenly the service is not available. Now we have this surge of users who want to call a Lyft ride. And these things change. They are changed based on real-time events. We also want to fix issues with fraud. We want to catch fraudsters in the act. And a lot of these patterns of usage that fall under that category also keeps changing with time. So the point that I'm trying to make here is that it's very important to provide the most real-time view of the world to our machine learning models for them to be effective. How many of you have read XKCD comics before? And those of you who haven't, I highly recommend it. It's hilarious. So this over here just cracked me up. I found this a few weeks ago. So the guy on the left asked, "Is this your machine learning system?" And the other guy, who looks like is sitting on a pile of garbage, says, "Yeah, we just pour data into this pile of linear algebra and hope for the results. And what if the answers are wrong? We just stir the pile." So that's exactly what we do. So this is the end of my presentation. Welcome to my tech talk. But in all seriousness, so when we wanted to develop this platform for online feature generation for our machine learning use cases, we had some needs in mind. So first was low latency computation on streaming data. That was really important for us. The second was we wanted to build a platform that was self-service and very easy to use. And one thing I'd like to point out here is that our main customers were going to be data scientists and research scientists. And they are more comfortable with languages such as Python, Go, SQL. In fact, most engineers at Lyft use Python and Go more commonly. We also wanted this system to be fully managed because we don't want our research scientists to worry about distributed systems and deployments and all that jazz. So with that in mind, let's dive into all the steps that we took to get to where we wanted to. So the first thing was we wanted low latency computation on streaming data. And for that, we decided to use Apache Flink. So why Flink? Because Flink provides the capability of low latency, high throughput computations on streaming data. Event time processing is supported, which was really important for us because then you would always get the same repeatable results even when you're replaying. We also wanted fault tolerance because shit happens in a distributed systems environment, but we want to recover gracefully. So Flink's checkpointing mechanism aids in that. And also Flink supports exactly one semantics, which is great. The second part was self-service. So how do we make a system that is easy to use by research scientists? So this is a very high-level overview of like the interaction and like the architecture of our system. So a user writes a user configuration. In this configuration, they tell us their logic. Like, this is the logic for my feature generation algorithm. Then they give it to our control plane, and our control plane takes it from there. So the control plane parses the configuration, performs validations, does any kind of enrichments that are required on the program, sets up logging, monitoring, everything. After that, it generates a job graph and submits it to our Flink cluster. Done. Now the program is up and running. It's producing real-time features. The features are being written to the feature store. And we provide a UI view to the user through which they can monitor it, look at the dashboards, logging, everything. And this is what a sample job configuration looks like. It's as simple as this. So all they have to tell us is that here is my program file where you can find the logic. This is my feature definition and any other flags that may be required to run the program. We use a lot of Flink SQL, so users can supply their logic using Flink SQL. Very easy to do. But not everything can be represented in terms of SQL, right? Like there can be complex processing that needs to be done, for which SQL may not be adequate. So for that, we wanted to allow the use of Python. But Flink doesn't support Python directly, so for that, we used this newfangled thing, I don't know, like it's called Beam or something, to bridge the gap between Python code and the Flink cluster. So now our users can specify write programs in Python, and Beam does rest of the magic. So this morning, Max and Thomas talked about this, so I won't spend too much time here, but once the user writes their logic, the SDK is, so the pipeline, the Beam runner takes this language-agnostic pipeline, converts it into a Flink job, and submits it to the cluster. The runner will then take care of setting up any like artifacts, setting up the SDK workers on the machines, and set up the fun services and everything. So again, from the user point of view, this is all abstracted away and really easy to use. Now coming to the deployment side of things. So in the current state of the world, we deploy our platform to AWS EC2 instances using Lyft's own custom deployment process involving salt stack. Separate auto-scaling groups for job managers and task managers are used. The instance provisioning is done at the time of deployment. So when we deploy our platform, at the time we make an estimate of how many jobs will be running on this cluster until the next deployment, what would their parallelism be, how much task slots they require, and based on that, we provision that many machines in the cluster. And one thing I'd like to point out here is, in the current situation, in the job manager ASG, we have one job manager that is managing close to 60+ jobs that are running on the task manager cluster. And what that leads to is multi-tenancy hell. Because of this lack of job isolation, it's possible for several different jobs to share the same task manager, and when one goes down, it can take the others down with it, and also the problem of one job manager to rule them all. So this is definitely not ideal, and we got ahead of ourselves to make self-service a higher priority. But now we are trying to fix that. One of the teams at Lyft has been working really hard to build the Flink operator for Kubernetes. So how does that work? So now, when the user gives us their job configuration, our control plane converts that into a custom resource descriptor, which we'll see in a minute. Then this is submitted to the Flink operator, and then the Flink operator looks at this custom resource descriptor, and it knows, and then it sets up the cluster according to our needs. So it sets up the cluster for that job with one job manager, how many ever task manager containers are required, and any other containers that needs to be started up. And then it launches the job. This is an example of the CRD, and this basically is a description of what should my cluster look like, and the Flink operator makes that happen. One of the other nice things about this, about the Flink operator, is that it detects changes to the CRD. So if it sees that something has changed in the CRD, then it starts the update process for the job. And the way it does that is it sets up, creates a new Flink cluster with the new updated CRD. It cancels the Flink job that was running with a save point, and then it launches a new Flink job with that save point in this new setup. So great. The best thing about this setup is job isolation, of course. So now we have one job manager per job instead of one job manager like running 60+ jobs. There is support for application updates, green-blue deploys, and it can scale to hundreds of Flink applications. Right now, this is in alpha stage, and we have been working really hard to get this fully into production. Now let's talk about some of the practical things that we had to deal with when we were building this platform. So I'll start with bootstrapping. So what exactly is bootstrapping? So for that, let's look at this simple Flink SQL example. So here, we want to count the number of rides a passenger took in the last 30 days. So I mentioned earlier that our feature generation Flink programs work on streaming data, and they produce features in real time. Our events are ingested by our pipeline and put into Kafka and Kinesis streams. So suppose we start this program, and it starts consuming real-time events as it comes in our Kafka or Kinesis streams. What do you think would happen? This program would need to run for at least 30 days before it has enough data to answer the query correctly. And that is not ideal. What if after 30 days, the research scientist decides that this is wrong and they want to test something else? So this is where bootstrapping comes in. So what we instead do is, like, instead of, when the program starts, instead of starting to read the events from that time, we look behind. We look behind at historic data, build up state, and then it keeps getting updated as new events come in. But there's a small problem with this. So at Lyft, our Kafka and Kinesis streams have a retention period of 7 days. So we can't rely on just that source to supply us with enough data to bootstrap the program. So for that, the solution that we came up with was to read from two sources. So at Lyft, all the historic events are persisted to our S3, to AWS S3, and real-time events are present in Kinesis and Kafka streams. So in a Flink program, we read data from these two sources, take a union of it, apply the business logic, write results to sync. And this works great. We have programs running on production. This is actually an abstract shape of the programs that are currently running on production. But this uncovered an interesting problem, which is related to source queue. So what exactly is source queue? So suppose you are consuming from your program is consuming from several different partitions. One of the partitions is producing older data, and the other partitions are producing newer data. So as the consumer reads these data, it's setting up, bucketing these into time windows and setting up state. But because old events are coming in, our watermark is behind. So we keep on opening up these states, but they are not closing. We are still waiting for all the old data to come and finish processing. So all these new windowed states open up, and this problem becomes even more dire when we are reading from two different sources. So like S3, we read historic data from S3 and new data from Kinesis. And the problem with that is, with these, the state size increases, which causes checkpointing issues, memory issues, and so on. So to solve this problem, the streaming platform team at Lyft came up with a solution to synchronize the sources. So how does this work? So now we have a shared state which contains the global watermark for all the consumers and all the partitions. So all the consumers report the low watermark to this shared state. So now if one of the consumers has like newer data, it's pulling in newer data from its partitions, it looks at this shared state and it tries to make a decision. It's like, when it looks at this shared state, it's like, oh, my watermark, the watermark currently is really behind, but the data that I have is really new, so it's possible that it won't be immediately used. So let me just wait for the watermark to catch up. And so the consumer waits, so now we don't have, so now our windows, so now once the old data finishes processing, the watermark advances, so our other consumer, which is processing new data, decides to pull more data and pass it to the next operator. So that's how source synchronization works, and I've attached some references where you can read more about it. So before I conclude, I wanted to talk about some of the impacts that we were able to derive from this setup that we have with Flink and Beam in our platform. So the first use case that I want to talk about is dynamic pricing, and Thomas touched upon it a little bit today at the keynote as well. So I mentioned earlier that we want to give a fair price to our passengers. And it depends a lot on demand and supply. And we also want to balance out our marketplace. So suppose in in the scenario when we have too many drivers but not enough demand, we drop the prices to balance the marketplace. On the other hand, when there is a lot of demand but not enough drivers, we raise the prices. So in the legacy pipeline, this feature generation for this was being done by the means of like several cron jobs. It was really complex, and there were high latencies. So before I go into that, so I want to talk about the scale of the dynamic pricing use case. So after we started using Beam and Flink, and remember that we are updating like millions of geohashes every minute with what we think should be a price multiplier for that geohash. After moving from the legacy pipeline, we were able to get latencies of 30 seconds. It was reduced from 30 minutes. So now the bottleneck is it's dominated by model execution. The model code that was being used by the legacy pipeline we could reuse that. The code complexity reduced greatly from 10,000 lines of code to 4,000. And we were also able to save up on instances. But our platform is being used not just for ML. It's being organically used for various other use cases that were a surprise even for us. So earlier this year, Lyft launched a program called the MasterCard Elite program. And the way it works is that we want to give rewards to customers who pay for their rides using their MasterCard credit card. So the growth team wanted to build this product where they wanted to keep a track of the amount of spend a passenger does in a month on the platform. And when they hit that spend, they immediately give them a reward. So they wanted to set up, they were looking at ways to set it up, and then they learned about the machine learning platform, and they decided to use Flink SQL to drive this product. So now they launched a program in our platform, and this program keeps track of the amount of spend that a user makes as a new event, a payment event for the user comes in. As soon as the goal is hit, a notification is triggered to the user, and they are given the reward. They were able to reduce development and testing times from 6 months to a month. It took them a month to test it, verify it in production, and roll it out. With this, I would like to conclude my talk. Thank you all for listening. And I'll be around, and Thomas, my colleague from Lyft, will be around as well if you want to ask us questions.